Have you ever just stopped and wondered what actually dictates the shape of a fluid? Like, why does a tiny dewdrop form this perfect little sphere on a leaf? But if you spill your water, it just flattens out into a puddle on the floor. As undergrad science students, I know you observe these kinds of phenomena all the time, but the answer isn't just random chance. It's actually the result of a constant, literal tug-of-war between two fundamental forces. So let's dive into this delicate balance, because understanding it, well, it's pretty much the key to unlocking how we're going to travel way beyond our home planet. Welcome to This Explainer. Today, our whole goal is to completely dismantle those Earth-centric assumptions you have about fluid dynamics. We're going to look at exactly what happens when the physical laws you've been learning in the lab are suddenly stripped of one massive variable: gravity. Get ready to shift your perspective on literally everything, from boiling water to deep space spacecraft engineering. Here's our roadmap for today. First up, gravity versus surface tension. Second, the microgravity boiling crisis. Third, controlling fluids with geometry. Fourth, validating theories in orbit. And finally, engineering for deep space. Let's get right into it. Section 1, gravity versus surface tension, the fundamental balance. Okay, let's start with the basics of this universal struggle. Surface tension always wants to minimize surface area, right? It pulls liquids into those tight, perfect little spheres. But gravity wants to minimize potential energy, so it just flattens liquids out. So who wins? Well, it depends entirely on the scale. And to understand this fundamental balance, we have to look at something called the capillary length. Think of this as nature's intrinsic ruler. It's the exact physical crossover point where the hydrostatic pressure from gravity is roughly equal to the capillary pressure from surface tension. For water, down here on Earth, this magic length is about 2.7 millimeters. If you're dealing with a droplet smaller than that, you're living in the world of surface tension. But if you have a volume of water larger than that, well, congratulations, you're officially in the empire of gravity. But consider what happens to a fluid in a container when we completely remove gravity from the equation. In the microgravity environment of space, your capillary length essentially becomes infinite. The force of surface tension steps up and becomes the absolute sole dictator of how that liquid behaves. If the liquid is just free-floating, it forms a massive sphere. If it touches a wall, it will literally violently cling to it and spread all across the surface. Gravity just isn't there to pull it down anymore.
Section 2. The microgravity boiling crisis, when buoyancy disappears.
Now, here is where the physics gets truly bizarre, and frankly, where spacecraft engineers start to sweat. Let's think about what happens to phase changes when we zero out gravity. Just imagine a standard pot of water boiling. Down here on Earth, bubbles of vapor form on the hot surface, and then buoyancy, which remember is just gravity acting on the density difference between water and vapor, pushes those bubbles upward and away. Simple enough, right? But in microgravity, there's absolutely no buoyancy to lift those bubbles. So those isolated bubbles, they just sit there. They grow, they merge together, and eventually they form a single, giant, stationary vapor bubble that completely blankets the entire heater.
And that brings us to a really crucial point. This lack of buoyancy triggers a catastrophic fluid dynamic crisis known as the critical heat flux, or CHF. Now, this isn't just a heater getting a bit too hot. It is a total phase change failure. That excessive vapor literally blocks the liquid from ever returning to the heated surface. And because buoyancy is basically non-existent in space, this CHF threshold is significantly lower up there than it is on Earth. That vapor forms a stubborn insulating layer that entirely chokes off heat transfer. Not exactly what you want happening in a spacecraft. So how do we fix this? Well, a really fascinating study out of Purdue University looked into flow boiling in microgravity using a dielectric liquid called FC72. They figured out that if you don't have gravity to move the vapor, you actually have to pump the fluid to inject some inertia into the system. As you push the fluid past those heated walls, three really distinct things happen right before you hit that crisis point. First, a wavy vapor layer starts developing on the walls. Second, as it gets thicker, the peaks of these vapor waves actually get drawn into the troughs of the opposite wall. They literally mesh together like mechanical gear teeth. And finally, the third step, they merge entirely. Understanding this fluid inertia is absolutely crucial because it's the only way we can actually control bubble growth without the help of gravity.
Section 3. Controlling fluids with geometry, the natural solution. Since we obviously can't rely on gravity to move our fuels and coolants around, and we really want to avoid relying solely on heavy, fail-prone mechanical pumps, we leverage something called interior corner flow. This is the capillary-driven migration of a fluid right along the intersection of two solid surfaces. Just think about it. If surface tension is the main boss in space, we can actually trick the fluid into wicking itself exactly where we need it to go, purely based on the shape of the tank itself. Spacecraft designers are incredibly clever with this, using this exact phenomenon to passively pump fluids. The real trick here is that if two solid surfaces meet at a narrow enough angle, fluids in microgravity will just naturally flow along the joint. No mechanical pumping required whatsoever. This is the exact same physics behind that famous zero-gravity coffee cup you might have seen astronauts drinking from online. But when you scale that concept up, it's exactly how we move massive amounts of cryogenic fuel and even recycle wastewater on the International Space Station. It's geometry doing the heavy lifting. Section 4. Validating theories in orbit, the lab in the sky. Now, having all the analytical math for these capillary flows is fantastic, but as science students, you know that theory always requires experimental validation. And that becomes a pretty huge problem when your lab is stuck on Earth. Listen to this incredibly crucial insight straight from NASA's capillary flow experiment documentation. The equations governing the process are known, but have not been solved to date because of a lack of experimental data identifying the appropriate boundary conditions. You see, we can use drop towers here on Earth to get, maybe 2.2 seconds of microgravity? But a large capillary imbibition process inside a spacecraft fuel tank might take 45 whole minutes just to reach equilibrium. You simply cannot test that on Earth. And that is exactly why NASA launched the Capillary Flow Experiment up to the ISS. Astronauts up there use these highly specific, handheld 1 to 2 kilogram vessels to gather high-speed video data on interfacial phenomena, which, by the way, is just a fancy way of saying how liquids, gases, and solid surfaces interact right at their boundaries. They test contact line dynamics to really understand sloshing, interior corner flow to measure those passive fluid positioning rates, and vein gap configurations to pinpoint critical wetting conditions. When you consider the low-G interface shape of a fluid inside a cylinder, you really have to look at both the macroscopic contact angle and that microscopic contact line, where the fluid, the vapor, and the solid wall all finally meet. Out in space, these tiny microscopic boundary parameters entirely dictate the massive overall interface shape of the fluid. Think about it. If a spacecraft does a maneuver, understanding that exact contact line is literally the only way we can predict how the fluid will slosh and ensure the stability of the entire ship. Section 5. Engineering for deep space, the ultimate payoff. Let's tie all of this together. All this theoretical physics, the boiling phenomena, the orbital data, it all directly comes back to the ultimate goal, which is keeping humanity alive in the cosmos. Any future exploration missions, say to Mars, are going to require way larger liquid propellant masses than have ever flown before. We are talking about massive systems completely reliant on fluid physics, cryogenic fuel storage and management, thermal control and vapor-liquid separation, closed-loop life support, and water recycling. Every single one of these advanced systems would completely fail without an absolute mastery of multi-phase and capillary flow. I mean, if you can't separate vapor from liquid in zero gravity, your life support system literally stops providing clean water. It's life or death up there. This is why the visual data gathered from the ISS is basically pure gold for engineers. It provides immediate, real-world confirmation of our analytical design tools. When we can actually verify these complex computer simulations, spacecraft designers can confidently remove those heavy, complex mechanical pumps. By relying on the passive capillary physics we've been talking about, they fundamentally decrease the spacecraft's mass and drastically increase the mission's reliability. So, as we wrap up, I want to leave you with a rather provocative thought. By mastering the micro-forces of fluid dynamics, are we actually unlocking the key to conquering the macro-scale universe? It is pretty incredible to think that understanding the absolute tiniest capillary action, or how a single vapor bubble meshes, is the exact thing that makes interplanetary exploration even possible. Thank you so much for joining me for this explainer. Keep asking those big questions, and as always, keep looking up.